Welcome to this online course on elementary differential geometry. So, in this course, we'll try to explore the ideas of elementary differential geometry. This is more or less an advanced undergraduate course in mathematics, and usually we'll require some basic knowledge from linear algebra. So the prerequisites for this course are linear algebra. In particular, we need to know about orthonormal basis, the SO2 matrices, that is the orthogonal or equivalently the unitary matrices. We also need some basic properties from inner products, and naturally where inner products are involved we'll have norms. Now these are some very basic prerequisite from linear algebra, nothing fancy about it. Another topic, another prerequisite for this online short course is from calculus, in particular multivariable calculus. So which includes Green's theorem, gradients, notions about the derivatives of functions of several variables. So these are some prerequisite courses which you need to be familiar about. Otherwise, you may find this course hard to digest. Okay, so moving on. We'll begin with curves. Now, intuitively, when we did high school geometry or even in calculus, we studied about curves like say the circle and circles are represented by the equation x square plus y square equals 1. So this is a circle of unit radius which will look something like this. I'm sorry, this is not a good picture. Yeah. So this is the circle of unit radius. Another easy and a popular curve which we usually talked about was the parabola, whose equation was given by y minus x square equals 0, and which had which looked something like this. I'm so sorry. This will be y. Okay. And last but not the least, we have the straight line whose equation was you can take as y minus 2x equals 1, which will look something of this sort. Now, these curves are defined by the means of Cartesian equations. That means we have a Cartesian coordinate system, we have an x-axis and y-axis, and we represent these curves in terms of a Cartesian equation, which if you observe carefully, is a function in two variables x and y on the left hand side, which is equal to some constant c on the right hand side. Okay, so this is a constant, and here we have functions of x and y. All right, so from this point of view we can say that a curve is a set of points where this set we can define as say c equals, here we have xy belonging to r2 in this case, such that f of xy is equal to some constant c. Uh, So, intuitively, a curve is a set of points xy in R2. R2, you must be familiar with, is just the xy plane we have, where this point C is given by the coordinates x, comma y. Now, given a function f, which is a function in two variables x and y, now all the xy's in R2 satisfying this equation will form the curve C. So, for example, the point 1 comma 0 lies on the curve x square plus y square equals 1. So we'll look at 1 plus 0, which is equal to 1. However, if you notice, 1 comma 0 does not lie on the line y minus 2x equals 1. We can surely verify this. So this gives us that minus 2 equals 1, which is a contradiction. Alright, so curve is a set of points which satisfy this specific equation. So later we'll look upon something known as the level curves. Now this you might have done in a multivariable calculus course, where the function levels itself to the constant c. Alright. Now another way of describing these curves is in terms of the coordinate they have. For example, if we take a parabola, say y equals x square, we have this parabola y equals x square. Now, if we need to find a point C naught on this curve, so according to our previous definition, this curve C is a set of all those xy's in R2 such that y minus x square equals 0. Okay. Now, in particular, for an arbitrary point C naught, which belongs to C, let x coordinate be t. Then, since C naught belongs to C, we have y equals t square. Therefore, a point C naught is given by the coordinates t comma t square. Since the standard notation for writing a Cartesian point is x comma y, so following that convention, we have C naught as t comma t square. So we can so since this point C naught is arbitrary, this holds for all C belonging to the curve capital C, which essentially means we have a function which maps us to R2, right? Now, notice a single variable is being used to define this function. So you see, the input domain is a single variable. So this gamma depends only on one variable, and hence this gamma is from some interval in R. Therefore, a function from I to R2 can be used to describe a curve given by its Cartesian equations. Okay, so the equation given by gamma is known as the parametric equation of curve C, and T is known as our parameter. Now later we will see that this has an intuitive development as well, and the choice of notation for the parameter as T can be viewed uh, as the position of a point on the curve at time t. So this will be used later to define planar curves, surfaces, surface curves, etc. when we will defining the tangent vectors, etc. So at that time it will prove to be more useful and will make much more sense. So the parametric equation for the parabola is given by this equation. So you see, wherever you find a function of one variable which maps you to R2 such that its coordinate is given by these, coordinates t comma t square, you know the image of gamma is the path traced by so image of gamma is the path traced by a point which satisfies the Cartesian equation of the curve. Alright. So the image of gamma is known as the trace of gamma. To make it clear and on formal basis, on formal terms, when we say a curve gamma of t, we are only referring to some function. It's a total abstract thing which we are talking and dealing about. Whereas if we are talking about the image of gamma, which is the same as the trace of gamma, now this will be a figure x. So this image you are seeing is the trace of gamma, whereas the curve is the equation t comma t square. So in formal terms, when you are given that gamma t is a curve, you should think of a parametric equation of some sort of this form, a comma b, which obviously depends on t. The image of gamma is given by the picture or the curve we draw on the plane. It's the picture on the plane xy. Right. So keep in mind that gamma is nothing but a function. Okay, and it's a special kind of function which we are using and referring to. So we are calling that specific kind of function as a curve. Now we'll define. So here comes a definition. A smooth parameterized curve is a C infinity map such that gamma is from I to Rn, or maybe for the time being we'll be dealing with R3 only, and later on we'll generalize ourselves to Rn. So for now, we'll use the definition I to R3, where I is an interval on the real and T is a parameter in the interval I which is mapped to, I'm sorry, so it is mapped to, now we are mapping to a coordinate on the R3, so the XY coordinates will depend on T, as we have seen a few minutes ago. Okay, so this is our definition for a smooth parameterized curve. Just for slight recall, if someone has forgotten what a C infinity map is, so a C infinity map is a function which is infinitely differentiable. All right, it is equivalently known as smooth as well. That means you can take any number or any number of derivatives, it won't blow up. Also, a fair warning, this I in R is an open interval which is not necessarily bounded. For example, in the case of parabola, our interval was from minus infinity to infinity to R2. So our gamma t was given by t comma t square, where t belong to the real. So this is clearly not bounded, and, but it can be considered as a open interval. So from now on, our curves will be smooth. Okay, so whenever I refer to a curve gamma, a parameterized curve gamma, I automatically mean it is infinitely differentiable. Okay, so one last thing, a fair warning, it's just a conceptual thing. This is a very important point raised to one of my own teachers, is that a curve may be smooth, but its trace is not necessarily smooth. So a classic example for this is the curve gamma of t uh, t cube comma t square. I don't know if we need to take a 0 or not. I don't. Maybe we can take this matter. And t belongs to open interval -1 to 1. So this clearly is smooth. You see, you can differentiate it n number of times. It doesn't matter. It's infinitely differentiable. However, if you look at the trace of gamma, you'll see it looks something like this. Now, this is a thing you can verify on platforms like GeoGebra or Desmos, anything. Now, if we try to write the Cartesian equation, Cartesian equation of the trace, then we have x as t cube, y will be t square, which implies that x square equals y cube, or y equals x 2 by 3. So now if we take the derivative of this equation, we will get a jump discontinuity at 0. That is the origin. Okay. So you see a very subtle difference between the curve and the trace. So you see that a curve is an abstract function which can be used to describe this kind of a picture. However, the exact Cartesian equation for this trace might lead us to a thing like this, where we get a jump discontinuity at the origin. Okay, so I would like to end this lecture here, and we'll discuss about curves and further topics later in the next video. Hope you probably gain something from this lecture and will be gaining from the subsequent lectures. Any kind of feedback, criticism, or suggestion is welcome. Thank you so much. Keep learning mathematics and keep enjoying mathematics. All the best. Signing off.